Okay, so this talk is basically about building a managed Kubernetes service using ClusterAPI. Why on earth would you do such a thing, you say? Well, I'm amongst friends. I'm sure I'm not the only person here who's attempted to build such a thing. But to provide a bit of context, I work for a company called Nscale, and Nscale are part of this new wave of cloud provider that are being termed AI neoclouds. I didn't term that. It's actually been termed by a company called, I believe, Semi-Analysis. They did a really fantastic write-up on exactly what being an AI neocloud means, what it entails, what the differentiator is. And the differentiator, of course, is AI. The demand for AI and AI-type workloads have changed the game a little bit in terms of what people require from a cloud provider. And it's an interesting time to be part of, as someone who's been involved in building cloud platforms, public cloud platforms for a number of years. It's impossible to challenge the incumbent hyperscalers, right? Even Microsoft and Google can't challenge the likes of Amazon. But AI and the demands of AI workloads have changed that quite a bit because people are asking for different things. It's also a bit of a primordial soup in terms of how people want to engage with infrastructure. There are many different tools, many different frameworks, many different types of hardware that are being introduced. Who knows how this is going to play out? At the minute, it's a very, very exciting thing to be a part of. And so there's an opportunity for a different type of cloud platform where if we can stick GPUs in the hands of people developing this sort of software, then they can build something interesting and do their science, do their research, do their AI, whatever else. So, Nscale. One of the challenges of building an AI neocloud is having access to power. The first site that we have, we call ourselves fully vertically integrated. So we own and operate our own data centers. The first installation we have is actually in the Arctic Circle. It's in Norway in a beautiful place called Glomford. The really nice thing about it is it's next to a hydroelectric power dam, which gives us a fantastic source of sustainable, clean, cheap, limitless, to a certain extent, energy, and that's great for driving the usage of GPUs. We are European-centric. We have other sites that we're also building out as well. So, we've got sites that we're in the process of establishing elsewhere in Europe as well as in Northern America. Here's a few more pictures. The site in Glomford is really interesting, actually, because it's a modular data center. So the actual racks with the servers themselves are installed in these repurposed shipping containers, and we kind of lash those together, and that's how we aggregate the infrastructure for our cloud platform. So it's a really interesting spot. But ultimately, what do our customers want? They want GPUs, right? And how they get access to those GPUs differs depending on their requirements. Like I say, it's a bit of a primordial soup in terms of how people want to access these things. We've got people who just want bare metal, so they just want the physical servers themselves. But quite often, people want things like Kubernetes or batch workload schedulers like Slurm instead, and on that, they can do their training, they can run their inference service, they can do whatever else it is that they need. But fundamentally, it is about, if you've got access to power and you can get some GPUs and you can stick them online, there's a solid chance right now that you'll sell them and you'll make a good amount of money doing so. There's typical things that people are going to expect from any cloud provider. The assumption with a cloud model is that you can have any amount of capacity as and when you need it, so timely provisioning is very, very important. It's got to be cost effective, it's got to be decent performance, it's got to be reasonably reliable, and you want to have some support as well. So what do we have in terms of physical infrastructure? It is already quite a mix. We've got a bunch of Supermicro and Lenovo servers. We're also mixed in terms of the GPUs that we have. So we're partnering with both AMD and NVIDIA. And so we've got a mix of generations of GPUs from both of those two vendors. AMD stuff is fantastic silicon. It's really interesting from a price-performance ratio. It's nice to see NVIDIA finally having a bit of competition. The networking is a whole other talk and a whole other topic unto itself. Building this kind of cloud platform is very, very different. It's a different type of workload. It's more like HPC, and it's more about keeping these GPUs fed with lots and lots and lots of data and trying to assemble a large machine out of multiple physical machines and multiple GPUs and kind of run workloads and do your training in a way that lets you orchestrate those at very, very high performance. So each physical server has got multiple 200 gig network interfaces. And then, we've got things like VAST and Ceph for different types of storage, obviously different tiers, different performance levels. And we make sense of all that using OpenStack. So yes, OpenStack is still a thing. We're still big fans of it. It gives us APIs to drive this infrastructure. It certainly requires some work, but again, what doesn't? And we're engineers, so we like making things complicated for ourselves. But it means that we can have APIs for creating virtual as well as physical machines, virtual networks, subnet routers, all that kind of stuff. And that means that as a cloud provider, we can provide access to physical machines, we can build a Kubernetes cluster, or we can build you a Slurm cluster on demand. all self-service. This is the product pitch slide deck, right? So this is what we've built. So the stuff that I'm talking about today is what's actually behind this. It's probably nothing too exciting or nothing too exotic in terms of cutting-edge features. We've built this service to be opinionated, and it is designed for AI workloads. The way in which people use Kubernetes clusters for AI is a little bit different. Tim mentioned it this morning. It's quite common to spin up a Kubernetes cluster, do your training run, shut it down afterwards. It's not like it's running a suite of different line of business applications for a period of time. It's quite often they're spun up for that specific workload and then turned off again. So that's the product pitch, and that's what it is that we've been working towards building. So this is at least the second Field of Dreams reference today only. This is the baseball field that is from Field of Dreams, the film. No Kevin Costner in this one. But to begin this story, I need to wind the clock back a couple of years. So about 2 years ago, myself and a few other people in this room today joined another startup, sadly ill-fated for a variety of other reasons that I won't go into. But the requirement there was to basically assemble a cloud service and build a managed Kubernetes service. And like any good open source citizen, I didn't want to just go through the whole not invented here syndrome. We wanted to look at what was already out there that could help us, give us a start and give us a decent foundation on which to build a managed Kubernetes service. So the two options really at the time were OpenStack is broken up into a multitude of different smaller sub-projects. There is a container orchestration engine as a service project called OpenStack Magnum. It integrates with OpenStack in the way you'd expect. You get a GUI. There's people who do use this successfully. There's the likes of CERN have been on stage at KubeCons previously. They do use Magnum quite successfully, but it's pretty weird. Magnum was originally designed generically as a container orchestration engine and service platform. It was designed to support not just Kubernetes, but also Docker Swarm and Mesos. So in some ways, it is unnecessarily complicated. There are more shell scripts than I would like involved in actually provisioning Kubernetes. And fundamentally, if you know OpenStack, it's got a dependency on a service called Heat, and everybody hates Heat, so it wasn't really an option. Rancher should be the perfect fit. I'd just come from Rancher before I joined this company. Know Rancher well. It's got APIs. It's literally the sort of thing that it does. It's a managed Kubernetes. It provides a managed Kubernetes service for self-service Kubernetes clusters. It's really mature. Everyone likes it. But sadly, the OpenStack support and the OpenStack side of things is very much lacking. I always thought this was a pretty big missed opportunity, especially now. The Venn diagram of people that want to use something like Rancher and OpenStack, I think there's a solid crossover there. But it was only ever community supported. The actual machine driver was based on the old Docker machine stuff. Didn't work particularly well. Missing a bunch of features as well, like self-healing and auto-scaling wasn't there. And there's also if you use Rancher, it installs agents in the clusters that it's managing. So it's kind of leaking implementation details in the way that didn't really feel great to me. So what else was going on? We took a look at what else is going on out there, and of course, ClusterAPI is quickly becoming a thing, and is quickly becoming very, very popular. So for the folks in the room that don't know what ClusterAPI is, it's basically a set of operators, or it follows the operator pattern, where you extend an existing Kubernetes cluster and you imbue it with the powers to manage other Kubernetes clusters. So it's perfect for building the kind of service that we're talking about today. You get a bunch of CRDs. They give you the ability to define the topology of a Kubernetes cluster that you want to manage. And it's kind of like Terraform in that it has providers, and those providers give it the capability to talk to the infrastructure APIs to create virtual machines, subnets, routers, all the rest of it. And the good news is that the CAPI provider for OpenStack is really well supported. There's lots of good companies out there making use of it, companies who I would respect, like Red Hat, Giant Swarm for a brief while until you gave up on it, Stack HPC. So yeah, it was good to see that, and it leveraged Go for Cloud, which is really mature. It's the same library that powers the Terraform OpenStack provider, works really well. So yeah, happy days, mature. Let's go ahead and build that. As a quick aside, because hindsight is a wonderful thing, fast forward 2 years, there are other projects that are doing very, very similar things. There's one or two that have already been mentioned today. So there was a talk yesterday on Stack HPC's Azimuth platform. It's doing similar things. There's now a CAPI driver for Magnum, so that might, could have been an option, maybe a contender at the time. Kamaji is doing sort of very, very similar things. And of course, there's the whole Sidero Metal, Talos Linux, their whole platform, which is, looks really compelling as well. But we built our own thing, because why not? So coming back to CAPI slightly, there are multiple components that are involved in ClusterAPI itself. There's the management cluster that I've mentioned. So this is the thing that you install CAPI into that gives you those CRDs, as well as the provider or providers. And then, yeah, the infrastructure provider is the thing that actually goes out and creates that virtual or physical infrastructure for you, as well as any dependencies. So it will create your control plane nodes. It will create your load balancer for the Kubernetes API. It will create all the network dependencies, that sort of stuff. Then we've also got to install Kubernetes, right? So there is a concept of a bootstrap provider. The default one with CAPI is good old kubeadm. It's about as vanilla and as standard as you're going to get. There are others. I'd love to see the K3S bootstrap provider, kind of get a bit better and see a bit more maturity. And yeah, there's others that are being worked on. So yeah. That's the bootstrap provider. And then finally, there's the workload cluster. So that is the cluster that is ultimately under the lifecycle management of ClusterAPI itself. That's the customer cluster. That's what you get as an end result. And as you'd expect, if you want to describe a Kubernetes cluster in CAPI terms, there's quite a lot of resources that you're going to have to instantiate. You can, of course, template this out, but as a minimum, you've got a cluster definition. That'll reference an OpenStack cluster definition in the case of something you're installing on OpenStack. There are specifics in there around things like the basic Kubernetes stuff, pod side ranges, service side ranges, all that kind of good stuff. You want to define a kubeadm control plane. So this is how many control plane nodes you want. They in turn reference an OpenStack machine template. So they describe the size and shape of the machine that you want behind your control plane. And then there's one or more machine deployments, and these are the workload pools. So these are the actual worker nodes that make up your cluster. And they in turn also reference the OpenStack machine templates. And then there's a bunch of others. So there's machine health checks. What happens if a node is offline for 10 minutes? Does it get replaced? Does the cluster self-heal? All that kind of stuff. So there's quite a lot of complexity, and this is the stuff that we as a cloud provider have to take ownership of. We've got to think about, to provision this as a service, what does the architecture look like? And then there's a lot of stuff that we need to finesse in terms of not making it too complicated for you, the end user, to consume this stuff. There's a very strange interplay in terms of credentials for how ClusterAPI and the provider for OpenStack talk to OpenStack on your behalf. We don't want to make that complicated for you. We want you to come along with your Google credentials or your GitHub credentials and just be able to provision and do your thing. And then there's also add-ons. So CAPI will just create the cluster for you. It won't install a CNI. It won't install a cluster controller manager. It won't install anything like GPU operators if that's the sort of thing you need. It won't install CSI plugins. Something else has got to handle that. There is work within CAPI to provide mechanisms for that, but certainly a couple of years ago, there wasn't really a good answer. So that's something else that we'll have to take care of. And there's plenty of rough edges that we would also need to kind of file off. But otherwise, great foundation. And there's benefits to doing this stuff if you're building a self-service capability for letting people build their own Kubernetes clusters. Because these are just Kubernetes resources, you can treat them like any other workload, so you can apply GitOps to it. There's been many other talks on this particular subject. You can obviously just template this approach using Helm charts, whatever else. It's also well supported by adjacent projects, so things like Cluster Autoscaler. You can plug that straight in, and you've immediately got cluster auto-scaling capability. And it's a well-considered cluster lifecycle model, so it has got things, like I say, around auto-healing, and the upgrades follow sort of standard Kubernetes approaches. The cons largely come down to a couple of factors. First of all, there's a set of problems that are just typical of like the operator pattern, where you have a custom controller that's managing a resource. Like, how well does it manage that resource? How well does it manage those edge cases? Kubernetes is great when it's in full control over the thing it's supposed to be managing, but if it's hooking out into external services and into an external service that doesn't sort of follow that, the Kubernetes model of declarative eventual consistency, it can be a bit of a pain if the service it's trying to reconcile will never reconcile because of a set of conditions that are outside of its control. That's kind of up to the quality of the provider itself to manage those, and there's some really awesome bugs that we hit very, very early on. OpenStack is designed so that you can have, you can create resources with the same name. Like everything in OpenStack, its uniqueness is tracked by UID. I think the people that were originally involved in writing the provider didn't really sort of get that, so assume that no one would ever create two clusters with the same name in the same project. It's perfectly valid, and we thought you could, until we deleted one of them. And then, as it happened, as it reconciled, it deleted a bunch of resources from the other cluster, so it took out the other cluster at the same time. So yeah, that kind of thing, all fun and games. Luckily, that bug has been fixed, but there's stuff like that that's lurking in there. And then, yeah, again, anything like this, if anything goes wrong, you can quite often be fighting against Kubernetes itself, and it's debugging can be a little bit painful. So, for us to wrap this up as a cloud service provider, we developed our own service. And the service, the open source project behind this is called Unikorn. Why on earth is it called Unikorn, you ask? Well, first of all, the project name was, we came up with that at KubeHuddle in Edinburgh 2 and a bit years ago. And as you may or may not know, the Scottish national animal is a unicorn. And then, yeah, but the main reason is because Sai, who's the primary author and primary developer on Unikorn, really loves unicorns. And I'm actually very surprised he's not wearing a unicorn T-shirt today, because that is rare. So yeah, and of course we gave it a K because, Kubernetes. But it lets us abstract away ClusterAPI. We automate that the whole installation and configuration. It's designed from a cloud service provider perspective, so it provides hard multi-tenancy by design. It's also multi-region aware, so straight away we can provision to multiple disparate OpenStack clusters if we need to. And it's comprehensive in terms of what we expose as far as upgrades and all the rest of it is concerned. Behind the scenes, it leverages a bunch of other open source projects, notably ArgoCD, as well as vCluster. It's got other things as well. It lets us integrate with, it provides an abstraction as an identity provider so people can bring their own credentials and makes things a lot easier, like I say, for us as a cloud service provider. It does a lot at this point. 8-9 months ago, I actually gave this talk at the Edinburgh meetup, and Unikorn was relatively simple. And since then, it's kind of ballooned in terms of scope, because obviously we're building something much more comprehensive at end scale. But I'm not going to talk about the whole piece. I think there's numerous parts of this we could probably spend at least half an hour on individually. So I'm just going to drill down on the Kubernetes components, because that's why we're all here. So there's a Kubernetes service. The green boxes represent a logical grouping. These break down into a number of microservices, but the Kubernetes service itself is responsible for two main things. It provisions a dedicated and isolated instance that is configured of CAPI and capo plus any dependencies, so things like autoscaler. And then it also provides a representation of what we consider to be an end-scale Kubernetes cluster. So just the configuration options that we would want you to care about. We've tried to keep it as simple and as opinionated as possible with a reasonable degree of flexibility. So just to kind of bring in a little bit and sort of, help people understand what it is and how Unikorn actually works. We start off with the same management cluster, and there's a handful of microservices plus a bunch of CRDs, because, again, it follows the same sort of operator pattern. And there's a few basic additional dependencies, so ArgoCD and Cert Manager. ArgoCD is the workload engine for all the resource management. So we do all the heavy lifting of reconciling and keeping track of different resources is handed over to ArgoCD. And then there's vCluster, which provides us with the isolated instances of CAPI and capo. So the cluster manager piece is the component that's responsible for essentially creating the application definition within ArgoCD that in turn creates a vCluster instance for us on this management cluster. Once we have a vCluster, that is another Kubernetes cluster that ArgoCD itself can then talk to. And so the cluster manager then creates the resources for CAPI and capo. So these are the CAPI components, the capo components, plus the configuration required, the authentication credentials, everything else that's required for capo to be able to actually create OpenStack resources. At that point, we've got a set of controllers related to Kubernetes itself, and they can then create the cluster resources within that vCluster. And so these are the actual CAPI representations of the Kubernetes cluster we want to create on your behalf. There are multiple instances of this, or multiple cluster manager instances. These are created dynamically behind the scenes. You as an end user don't care about them necessarily. We actually create them. We have our own sort of hierarchy of like organizations and projects. They're created on a per project basis, but that's the kind of thing that happens behind the scenes. And then eventually, so you've created your Kubernetes cluster definition. Argo's gone ahead and translated that into the actual CAPI and capo resources themselves in the vCluster. And then that'll then take care of reaching out to OpenStack and creating the workload cluster, so the actual cluster itself on which your applications and services are going to run. And then finally, once that cluster is up and running, that also exists as a target that ArgoCD can also talk to and provision things on our behalf. So the Kubernetes services can once again create additional resource definitions or application definitions in ArgoCD that then in turn provisions any add-ons that we want. So we bootstrap it with Cilium, we bootstrap it with the OpenStack Cloud Controller Manager, so you get proper load balancer services when you create a service type load balancer. Any other drivers that we need, the AMD device plugin, the NVIDIA GPU operator, whatever's required. And obviously that gives us the opportunity to have business logic in there that makes sense of only conditionally install the NVIDIA operator if it's a cluster that has NVIDIA GPUs, that kind of stuff. It's got a really high quality API because one of the design goals of this was to make it easy to build stuff against. We've got a fantastic front end that's been built against this, as well as developer tooling that you'd expect, so Terraform providers and CLIs and all that kind of good stuff. Uses OpenAPI, which means it's really easy to auto-generate a lot of this stuff, and then it means it's also very, very easy to consume. We can also even auto-generate reference documentation, which is also useful if people want to build stuff against our platform. And it means that we can finesse that whole provisioning process. So that means that we've got a whole bunch of complexity behind the scenes because managing Kubernetes clusters for this kind of thing is complicated. But we can slap a really nice front end on it that really distills down just the specifics of what's required to provision that cluster in the first place. So right now, as pretty much a minimum, it's about 4 clicks to create a cluster. You select a region, you select a version, you define one or more workload pools, you hit go, you'll get a cluster with bare metal worker nodes. And I mentioned the automation piece. So you can't just have a fancy user interface. People want to do infrastructure as code. We've got a CLI. There's a Terraform provider that is well out of date that needs rewriting. I've just realized that refers to a very old repo. But it was a thing. It just needs resurrecting a bit of love. We'll get around to it. As anyone here is probably aware, though, like that part of the whole process is only it's the tip of the proverbial iceberg. There is a lot more to think about. There's a lot more on the data operational side. How do we handle things like upgrades? You've got to think about the components that I've mentioned because we want to upgrade CAPI and Capo because they obviously see relatively frequent releases. There's the actual cluster itself, like if someone wants to upgrade from 131 to 131.1, if there's a security vulnerability or they want a newer version. And then there's also all the applications that we have to manage on top. Like we're going to take care of those and provide you with a supported configuration. We've got to make sure that stuff works. The security side as well, we've got to think about and ensure that people, once you have your cluster, it is your cluster. It's a very big foot gun. You can do with it what you like. We want to make sure that you have at least a reasonably secure starting point. There's things like operating system images, which are the building block of the cluster itself. And then, in the spirit of support, we want to make sure that it's properly tested and that everything works repeatably and reliably so that what you get when you click go after your 4 clicks is what we know you're going to get. So upgrades are a fun one because you have to do what you can to push your customers along. People don't like to upgrade. Once they provision a thing and it works, they'd rather leave it alone, which is understandable. But the reality is, in this part of the industry, things move very, very quickly indeed. It's less of an issue for AI-related stuff, in my experience, because of what I mentioned before. Clusters tend to be relatively short-lived. So, it's kind of fine to be a bit more laissez-faire with like an upgrade strategy. But at the same time, CAPI does provide a lot of flexibility around how upgrades are handled, but there are some complications to it. So we've also had to write a few smarts in there that kind of take that, handle that on your behalf. We have an auto upgrade mechanism, which you can opt into. We support the 3 most recent versions of Kubernetes. As that last version falls off, you have a brief window in which you can upgrade yourself if you want to. Otherwise, we will upgrade you. And all being well, assuming that your application is a well-behaved cloud-native citizen, it should be fine. And we've also got a separate abstraction that handles things like the cluster manager upgrades. So that's the CAPI and Capo components, plus any other application bundles, which are the stuff that get installed in your cluster. And then, operating system images. So again, these are non-trivial, especially when we're dealing with bare metal hardware that is relatively exotic. We've got the Broadcom NICs, the multiple 200 gig interfaces that I mentioned, are really picky about the version of the driver and the version of the kernel that's installed. And it takes a long time to test this stuff on bare metal. These machines have got terabytes of memory. They take like 20 minutes to post. It's a real pain in the butt doing this stuff. So there's a huge amount of work that has to go into making sure that we build an image, it's got the right drivers, it all works as expected, it's standardized, repeatable, auditable. Again, there's a good starting point there. And Image Builder is an adjacent project. It has templates for building images that are then suitable for consumption by ClusterAPI. We built a project on the back of that, and now the basking shark picture makes a bit more sense. we built a project to kind of wrap that up and to give us a few other things as well. So Basky, build and scan Kubernetes images. Again, naming things is hard. And it's a wrapper for image builder and for Trivia as well. So we can build a container image. We do sensible things like pre-pull container images for the other stuff that we deploy to speed up that provisioning time, disable any unnecessary services, add any packages, any additional drivers, all that kind of good stuff. It boots it, it scans it, spits the output as a CI artifact. We can review that. If we decide we're happy and we publish it, then it gets signed and then it's picked up automatically by Unicorn. The testing piece is taken care of by another piece of software called Dogcat. And that gives us, it's like an end-to-end testing framework. So that will boot a cluster using Unicorn. It will install some real workloads on there just to make sure that the basics work. Can I create persistent volumes? Does that work? Can I create a load balancer? Does that work? All that kind of stuff. Put it through its paces a bit. I think eventually we'll deploy more workloads that are a bit more representative of what customer use, but at least that gives us a good functional kind of, we know this is good. We can go ahead and publish the updates. And then, so monitoring, there's a lot going on. One of the tools that we found invaluable that we've built into Unicorn is OpenTelemetry, so we can use a service like Jaeger to then make sense of what different API calls are going on. There's lots of microservices, lots of things that are being called in and out of the cluster. And there's basic things that we want to ensure, right? So when you provision a cluster, it should take a finite amount of time. We've got a service level objective. We want to make sure that it's meeting that. The clusters themselves, once they're provisioned, are essentially black boxes. We've no idea what's going on inside your cluster. It is your cluster. So we have to build stuff that sits around the outside so that we can make sense of, making sure that things are performing as they should be and monitor your classic your classic latency errors, traffic saturation, and sustainability, as we found out this morning. It would be really nice to see tracing. It's probably an idea to try and push something upstream for Capi and Capo. Would be good to see what happens as it's making calls against OpenStack. Could be quite useful. And then, non-functional testing is massive. So making sure that these clusters perform as they should do is something that we've put some amount of work in. Again, luckily, there is plenty of prior art there. Stack HPC have got a kubeperf test operator that gives you a bunch of CRDs that describe classic HPC synthetic benchmarks. So it gives you a very easy way of running certain benchmarks in a cloud-native way. That's been really useful. They gave a good talk on that last year, so we've been making use of that a fair bit. And so, I think I'm very close to time. I'm just going to quickly wrap up. I guess the takeaways from this is that ClusterAPI, although it's powerful and complex, it is a great foundation for building a managed Kubernetes service for companies like ourselves. We built Unicorn to scratch our own itch. It's got an extensive and exciting roadmap. And I guess the only selling thing that I'm going to have today is that we are hiring. So if this kind of thing is interesting to you, and you want to help us build next generation infrastructure for AI and related services, give me or one of the members of the team a shout. And that's all I've got for you. Thank you for coming.